Part 5, springs. Now, we've already talked a little bit about spring potential energy, but let's go ahead and well, I guess make it a little bit more specific, shall we? So when a force is placed on a spring, in other words, it has been stretched or compressed from its equilibrium length. We state this with Hooke's law. So when a force is placed on a spring, its force is proportional to the distance stretched or compressed. Okay, and so we can look at that from an equation where spring force is proportional to x. X means the distance stretched or compressed from equilibrium. Now, the actual equation for it, okay, is spring force equals kx, where k is the spring constant. Talked about this earlier. K is the spring constant, which discusses how stiff a spring is going to be, how much force it takes to move it a meter, and x is the distance stretched or compressed. Okay, now you have to be careful with x because sometimes in a question you're given, let's say, the length of the spring and you stretch it to this length. Well, what do you have to do? You have to subtract those two, right? So sometimes you have to be careful about what x is. X is the distance stretched or compressed from the original length, okay? Now, recall the other equation that we do end up using is also the spring potential energy equation, which is 1/2 times kx squared. So let's take a look at an example down below. It says, number one, a 200-gram mass is hung from a spring and it stretches from 7 to 15 centimeters. First, what is the spring constant? Then, what is the energy stored in the spring? Then, what is the change in gravitational potential energy of the spring? Then finally, what happens to the rest of the energy? So let's talk about that. Okay, so let's actually draw a picture. So this is the spring, okay, and when you hang a mass on the end of it, okay, let's look at the forces acting on that. You have the weight, and going up, you have the spring force equals kx. And so for part A, we're going to be using Newton's first law. Because we can see we have two forces that are in equilibrium with each other. The spring force is suspending the weight. So force up equals force down. Or kx going up equals mg going down. And you're solving for k. K is the spring constant. So k equals mg over x. Now, again, this is where you have to be careful because x is not 15. No, instead, it was stretched from 7 to 15. That means x is the difference between these, or in this case, 8 centimeters. Okay, so when we plug in, we're going to plug in 0.200 because we have to change grams to kilograms. So 200 grams, move the decimal 3 places to the left, is 0.200 kilograms. And then over here, 8 centimeters, right, is 0.08 meters. We've got to convert that as well. So got some conversions to do here and there. Again, I'll multiply by 9.8, divide that by 0.08. 0.200 times 9.8 divided by 0.08. And we should get about 24 and a half. We'll just round it up to, let's say, 25. 25 newtons per meter is our spring constant. The higher the spring constant, the stiffer the spring is going to be, the more rigid it's going to be, the harder it's going to be to force it from its equilibrium position. The smaller the spring constant, the looser the spring, the easier it is to stretch. Part B, what is the energy stored in the spring? Well, that would be the spring potential energy. So that one is a straightforward calculation. We're going to go 1/2 kx squared, 1/2 times 25 times 0.08, the distance stretched, squared. Now start with the 0.08 squared first. Then times 25, then take half. And you get 0.08. Now the unit for any kind of energy is the joule. Okay, and that is abbreviated with a capital J. Capital J stands for joule. Joule. Part C, now for part C, we're looking for essentially the change in gravitational potential energy. So the change in gravitational potential energy is going to be mass times g times the change in height. Well, so we're going to go 0.200 times 9.8 times 8. Now, technically, it's negative because you did drop. The potential energy does decrease because it ends up dropping, but I just wanted to point that out. Okay, and we end up with about 0.16 joules. So now the total energy, the question didn't ask you to find this, okay? But let's say I asked you to find the total potential energy. Well, what would you do? You would take those and you would add those together. Part D, what happened to the rest of the energy? So if you were to add those two together, okay, the total energy, the total potential energy, 0.08 plus a negative 0.16 is about negative 0.08, right? That's the total energy. So the total potential energy is negative. Well, what does that mean? Well, remember what we did here, okay? I'm going to do part D. There we go. Let's just go ahead and type it in. Okay, so now the idea is that the overall, or I say the total potential energy, right, is negative 0.08. It's the sum total of your potential spring potential and your dropping change in gravitational potential energy. So basically what happens is we lose more gravitational potential energy than we gain stored energy in the spring. Okay, and so what does that basically mean? It means that, remember, potential energy is the potential for some force to do work. So what does it mean? It means work was done by lowering the mass slowly. So the work was done by, the person's hand or whatever. The work was done by the upward force to prevent the mass from just simply falling and oscillating up and down. So the mass was basically allowed to stretch slowly and then, comes to equilibrium. Okay. But there was work done by the upward force from the hand, right, in lowering that mass slowly. That's what accounts for that negative potential energy. Okay, and question 2 here has a spring launched type question. Um, we're not going to go ahead and work this calculation only because we're not going to go variable only. No numbers are provided in the question, so we'll go ahead and skip it for the time being. So just go ahead and cross out this example number 2 right here. Okay, scrolling down, part 6, power. Power is the rate at which work gets done. Okay, what that basically looks like is this. You can kind of write it with an equation. Power, by the way, is measured in watts, so P is power. The unit is a capital W called watts. And you could reason out power as work divided by time. Remember, rate means you divide something by time, right? But look how else you could write this. Work, if you remember, was force times distance over time. And you guys might recall that distance divided by time is speed. So force times the speed is another equation. So we have 2 different power equations that we can use. Work divided by time, or force times velocity. Okay, so use whichever one corresponds to the question that you're working on. So for instance, in the example, it says how much power is needed to accelerate a 1,600 kilogram mass from rest, so V naught is 0, to a speed of 26 meters per second in 5 seconds. So what are we thinking here? Well, first we could find the work, okay, and then we could divide it by the time. So work, we could use work energy theorem, and work is equal to the change in kinetic energy, which means work is equal to K final minus K initial 0, and the work is equal to 1/2 mv squared. So we can find that. So 1/2 times the mass, which was 1,600, times the speed, 26 squared, that's going to be the work that was done. So 26 squared times 1,600, then take half of that, and we're looking at about 540,800 joules, right? Now, how much power is going on here? Well, power is equal to the rate at which the work was done. So it's 540,800,000 joules in 5 seconds. Remember, the less time that something gets done, the more powerful it is. In which case you're looking at about 108,160 watts. Remember, joules per second is a watt. Okay, and we're going to go ahead and cross out part 7. We're not going to be looking at gravitational potential energy to be visited. So That right now, ladies and gentlemen, concludes our notes for work and energy. I hope you found it helpful to get initiated with the topic. Again, I don't expect you to completely understand everything we do with our notes, but becoming familiar will help you when it comes to what we do in class together. So again, remember to pause or rewind any part of this as you need to. And of course, be prepared to come with as many questions as you feel you have during the lessons to come. Thank you.